Hi. I think we are on time, so we will start. Following Bill Mills' presentation today, we will give you a bit more details on the Virtio message over FFA specific use case. And Viresh will give you some update on the current state of the implementation and the different problematics we encountered. So, yeah. You've seen these slides in Bill Mills' presentation, so I will be a bit quick on this one, just for people who are not there at Bill Mills' presentation. So Virtio-msg is a new transport in the Virtio ecosystem, sitting alongside PCI, MMIO, and Channel I/O. It's a message-based transport, and it is designed for broad applicability, so VM to VM, secure world to normal world, and system to system, and so on. And it follows a layered architecture where you have a common transport layer, which is transforming requests from drivers into messages, and a bus layer underneath, which is communication specific or communication medium specific. So today, in this presentation, we'll go a little bit into more detail on the FFA specific use case that Bill mentioned earlier. So how did all this started? So this started from a use case. On this slide, you can see an Android system. On the Android system, you have an host OS, which is hosting the Android that we all know, some PVMs, and a TE. All this is running on top of pKVM. So compared to what you might know of an Android system as it is running now, where there is no PVM, some blocks have been extracted from either Trusty in the TE or Android and put into PVMs. So on this system, Virtio provides a transport mechanism that connects these components and through which those components are communicating. And Virtio message over FFA is used to communicate between PVMs and the TE or the host OS and the TE. The main goal from Google in this is to split a little bit the components so that there is a better separation between software components provided by SOCs and OEM providers and software components provided by Google itself. One of the goals here is to have a better way to provide software update, for example. So how does this work in practice when Virtio message is used over FFA? So first step is the Android host will create a PVM. That's step one. When this PVM is coming up, it will try to find out if there are Virtio message backend available. So this is going through FFA and a protocol UUID that is specific to Virtio message over FFA. On the steps 3, the PVM guest will create a Virtue and share the memory with the trusted environment. And on step 4, the PVM and the trusted environment will talk through Virtio message, apps can open dev-tipsy, and this is building a full communication system between PVM or host and between the PVMs or the host and the trusted environment, which is completely independent of whatever is going on underneath. So all this is built into using 3 main blocks. The first one is Virtio vSoC, on which all the trusted AL communication is built now in Android. Then you have Virtio message generic transport. And then for communication with the secure world, we are using FFA. For communication between PVM and the host, Virtio is still used, but FFA is not used at the moment. So Virtio message over FFA leverage some key features that have been introduced in FFA version 1.2 specification. The first one is UUID-based communication. So we use UUID-based protocol discovery so that we can have a seamless way to discover endpoints that are hosting a Virtio backend. Then we use direct or indirect messages to transfer messages. So that depends on what is available on the different endpoints or what the different endpoints are able to communicate with. And then we use extensively memory sharing to map virtues and DMA buffer into the remote endpoints. And this is to allow an efficient communication using zero copy. So how does this work in practice? So in this model, FFA is becoming the Virtio message bus. So discovery starts through, discovery starts through the FFA partition info get API. We use this to discover what endpoints are providing the Virtio message backend UID. And then with the answer to this request, we get if the other endpoint is able to discuss either direct message or indirect message or both. Then from that point on, we use only messages to communicate with the other side. So the first one is an FFA-specific message to negotiate a version of the protocol that we will use to communicate between the two endpoints. And then we use the generic bus message get devices. This is a way to discover what devices are provided by the backend. And then for each devices, we request the device information. That's mainly the vendor ID and device ID. With this information, the FFA bus driver is able to register the device into the operating system, and then the standard probe from the Virtio driver corresponding to the device is called. So Virtio net, Virtio block, Virtio vsoc, and so on and so forth. From that point on, all messages are transferred through the FFA bus driver by the generic transport layer. This is access to Virtio configuration space of the device, the Virtio features, setting up virt queues, and so on and so forth. And also event messages are transferred through messages in FFA. Then we have the memory sharing. So this is key to have good performance in Virtio. So when the transport or the drivers on the front-end side needs DMA buffer, shared buffers, or virt queue, the front-end will use FFA to share this memory with the backend. It will then send a message to the backend to inform it that there is a new area available using the FFA handle so that the other side can use the FFA memory retrieve API to get access to this memory. When the memory is not needed anymore, FFA APIs relinquish and reclaims, depending on the side, are used, and the memory is then only available in the front end. Yeah. What did I do? Sorry, going the wrong side. We also have support for dynamic devices discovery, which means when the backend has a new device appearing, it's sending an event message to the front end to tell it that a new device appeared so that the front end can register this device. This is providing us a fully dynamic behavior, which means that devices do not mean to be there when either the front end or the back end are created. They can be created dynamically, which gives us a behavior corresponding to what you have in existing Virtual transport like PCI. Viresh. So Viresh will give you now status on the implementation.
Good morning, everyone. I'm Viresh Kumar. I work for Linaro. So for the last couple of months, we have been developing the whole Virtio message stack in the kernel, and I'm here to present the status update for that. So during the early development cycle, a lot of components were missing. It was almost impossible to test, even if we write a generic Virtio transport. For the last couple of years in Linaro, we have been working on a project called Project Stratos and Project Orco, where we were working on Rust-based hypervisor-agnostic backends for Virtio, which are pushed in GitHub in the Rust VMM space. At that time, we also developed Zen vhost front-end repository for Zen to support Virtio MMIO and trapping all the requests and talking to the backend. That was already done. So now that there are two parts of the whole Virtio message thing. One is the transport, which is generic and bus agnostic, but then we have FFA or other buses which at the bottom. But there were no buses available which we could have tested initially. So what we did was we leveraged the Virtio MMIO support. So in Virtio MMIO, each device gets 5 and 2 bytes of configuration space, which gets trapped at the host side. So we implemented a Virtio MMIO bus beneath the Virtio message transport. And with that, we were able to transmit the Virtio messages, which were getting trapped at the host side in the Rust implemented Zen vhost front end, so that way we sent the messages back and forth. And this unlocked subsequent development over the work we have done for others too. The next step was to implement a FFA bus for us. So Bertrand here, he implemented Zen support for indirect messages. That was the first step where we can test the message passing between Zen VM and Zen host. This was without memory sharing at that time. Because this was indirect messages, the upstream status of the Linux kernel was that it only supports FFA direct messages. For that, in order to test Bertrand's patches, we picked some out of the tree patches from Sudeep, from ARM. They were mostly untested. We added a lot of fixes over them to make it work, but it finally worked. As I specified earlier, we had Rust-based hypervisor agnostic backends for I2C GPIO earlier, and we tested those simple backends with this setup. But memory sharing over FFA is still pending, which is one of the big deals. And that was the next step. One of the main use cases of all this work is to enable AVF to run isolated virtual machines and let them talk over Virtio. We have secure partition there, secure partition manager there. It can be Hafnium or AL2, or if that is not supported, we can have SPMC. Then we have trusty, which is running on the secure partitions. Now, we are using Virtio message over FFA for host or VM to talk to the secure partitions. Here. And with Virtio message Linux implementation with FFA, we finally were able to test direct messages between host and secure partition and pVM and secure partition. Google is also testing verifying. Some of that is already done and some is on the way. pVM trusty to secure partition trusty and pVM microid to secure partition trusty. Now the last part, memory sharing. This is one of the most important part which was not tested until now. And we have tested that finally with Google setup. Now there are two type of memory sharings we can do. One is something like Zen grants, where the memory is mapped on the fly as and when it is requested. But the major drawback of that is that there is a huge latency of mapping the memory every time you have to map a buffer. The buffer can be just 4 bytes, and you have to do the entire thing to map and unmap the buffer. So that is dynamic mapping. What we went for is static mapping. In this, we have reused kernel's existing device tree infrastructure with reserved memory and memory regions for FFA nodes, with which we can allocate a big enough pool of memory at boot time for a particular device or bus, FFA bus. And with that, all the DMA coherent operations that happens for a device, they get allocated from that particular memory itself. Other operations where you k-malloc the memory and then use DMA streaming APIs to map them, they get bounce buffer from them. The drawback here is that we may have potentially unused memory and we have to allocate a big enough chunk of memory in the beginning, but the good thing is that we don't have to map it again and again, and it is much faster. Yeah, that's it. Any questions and answers? We still have some time.
So this is a generic Virtio-msg question. So since you only define the transport and not the bus implementation, and how are you going to standardize the bus implementation? Because I'm writing a bus, PCI bus for Virtio-msg, and there is already a Virtio PCI transport. I mean, with the existing spec, kind of. But so how do you? How can we standardize things? I mean, with this and that.
The goal here is to standardize what a bus should provide as features. What we do in the Virtio-msg specification, so in the transport, in the Oasis spec, is for use cases where we think that it makes sense to define a common message that will be reused by transport, we specify it. It's always optional. We cannot really standardize the bus layer. The bus layer is meant to be adapted depending on how you transport the messages. It might be that several bus implementation will reuse exactly the same messages. That's what the FFA implementation does. We use the bus message get device, bus message device added, removed, etc., which are standard messages defined by the spec. But then we have specific messages because, for example, in FFA, when we share memory between the front end and the back end, in the FFA protocol, you get back on handle, which is a 64-bit value, and we need to communicate this value to the other side. This is fully specific to FFA, so it cannot be standardized in any way. So I created a specific message for that. We transfer the handle on the other side, but this message does not make sense for a bus that is using for IMP bus, for example, where they don't have those kind of problematics. So the goal is definitely to have a as thin as possible bus layer, but not to enforce too much so that you could do an implementation over almost anything.
Yeah, I mean, that perfectly works for new buses like FFA. But what about the existing buses like PCI? Because there are already existing Virtio-PCI devices, which is using the old transport.
We are not meant to replace the Virtio-PCI transport.
Right.
As said, the Virtio message transport is a new solution sitting on the side. There are cases where it does not make sense to use Virtio message, and it does make sense to use Virtio-PCI. For example, when you use Virtio for real hardware devices where you have a PCI bus and a Virtio net hardware implementation, you will use Virtio-PCI, you will not use Virtio message. So we provide a bunch of solutions to adapt depending on the cases. Yeah.
Yeah, and the problem is that for my use case, I cannot use the Virtio-PCI, but my underlying bus is still PCI, so.
Right, so, and I talked about this in my presentation, so the AMD solution is, so yes, the other system appears as a PCI endpoint, but there's a very thin layer there that says, oh, I know that PID and VID, and I know that my message data structures are going to appear in this bar region. And that's the end of the, and this is how I poke the doorbell. You don't have a doorbell, but this is how I poke the doorbell. And this is the number of MSIs I expect and what I'm going to map those to. That's the extent of the layer, and then it calls into the common AMP bus definition. So there's a PCI endpoint specific driver that instantiates the AMP driver that then instantiates the common transport. And the fact that you're over PCI and that there's a thing called Virtio-PCI, those are sort of two, those don't correlate. If your hardware can actually implement Virtio-PCI, then that's interesting. But if you're talking to software on the endpoint, then Virtio message is what you want.
Okay, in that case, I can have this PCI bus driver under Virtio-msg.
So if you look at our sample code, the AMD use case, there's they call it the Sapphire driver, and that it's doing the job today. As I discussed with you earlier, we're going to update the data structures for sending and receiving the messages, but their Sapphire driver is what I expect your driver to look like.
One intent that we have is to kind of standardize how you can transfer the message if the transfer possibilities that you have is a bunch of memory accessible to both sides and a way to send events. This way we will, for this case, that's the IMP use case, but we have other use cases. One of them will be FFA in the future. We want to standardize how you organize and how you use this shared memory so that we can share this code among several bus implementations. And the idea in the future will be to have this as a common library somehow that will be reused by the IMP driver, that will be reused by the Xen driver, because in Xen we have ground tables and events. We have no way to transfer messages between two guests, which means the only way that we have is create a shared memory and use this shared memory to store a file of messages to be transferred on both sides, which at the end is exactly the same case as the IMP case. You have some memory, you can transfer, and then you can send events. So we will try to standardize this in the future so that this part can also be a common part available somewhere that you can reuse in different bus implementation. This will also thinner the bus implementation effort.
Okay. And we're talking, so we haven't done it yet, but we're talking about adding that as an appendix
to the
to
virtual
the
spec.
Virtio spec. So here's some common data structures that many implementations would use.
Okay. Thanks.
So one question about your backend
Mhm.
or software or whatever it is. So assuming one would have a hypervisor now and would want to integrate the whole setup with the sort of Linux to Linux, so Linux being front and then backend. Do you have any sort of POC or of VMM or whatever you want to call that acts like a VM backend for the?
Yeah, we have. So what we have is a Zen-based setup where you have Linux Zen guest talking to Linux Zen host
Yeah.
and doing the tasks.
And
there.
what's running in the host? So for
Linux.
example, if I want to do a Virtual-FS or whatever, what would I need to run there to kind of provide the files?
So they have Rust VMM-based
Yeah.
components.
Okay, so
Edgar has QEMU running. So
okay.
both.
Right.
So the intent is that QEMU will gain Virtio-msg support. And we are working on defining how the bus implementation should be done so that you can have a standard QEMU which is discussing with any possible backend bus implementation in the kernel.
But you already have some sort of demo?
We have some POCs based on QEMU for Edgar and AMD and Rust VMM. And we are working on looking at reusing the Rust work which was done by Google to have a Rust VMM inside Opti too.
And where would one find such?
The demo, Chris from here, he will show you
Okay, good.
tomorrow.
That's the next presentation actually.
Okay, good. Thanks.
And we can also provide the Rust scripts.
Yeah. Any other question? We still have time if you want.
Guess you're quick.
Yeah? There was not much to say. It's so simple.
Okay, thank you.
Thank you, everyone.